Assalamualaikum everyone. We are from CDCS 143 and we will be talking about logical equivalence in this video. So, what is logical equivalence? Equivalence is a concept in logic where two statements are considered equivalent if they always have the same truth value in every possible situation. Even though the statement may look different, they mean the same thing logically. This means that whenever one statement is true, the other statement is also true. And whenever one statement is false, the other statement is also false. Logical equivalence show that difference in wording, symbols, or structure do not change the meaning of a statement. As long as the logical condition it describes remains the same, this concept is important in logic because it helps in understanding, rewriting, and simplifying statements. Logical equivalence is also important in mathematics and computer science because it helps simplify logical expression and improve logical reasoning. Next, we're gonna be talking about the background of logical equivalence. So, for the background of logical equivalence, logical equivalence became important through the development of formal logic. This development was strongly influenced by philosophers and mathematicians such as Aristotle, George Boole, and many others. In the 19th century, George Boole introduced Boolean logic, which laid the foundation for Boolean algebra. Boolean algebra is heavily based on the idea of logical equivalence, where different logical expressions can have the same meaning. As you guys can see, this is the picture of George Boole. Today, logical equivalence play an essential role in many fields, especially in computer science, digital circuit, and mathematics. It helps in simplifying logical expression and improving logical reasoning, making it a fundamental concept in modern technology and problem solving. So now we're gonna talk about forward and backward method. But firstly, the forward method. In the forward method, we begin with the original logical expression. Then we apply logical equivalent law step by step to simplify or transform the expression. Each step follow a logical law, ensuring the meaning of the statement does not change. If we can successfully transform the given expression into the target expression, then the two statements are logically equivalent. As you guys can see from the example above me, P implies Q, but when we apply implication law, it will become not P or Q. So now, for the backward method. The backward method, we start with the expression that we want to prove and work backward using logical equivalence law. We transform this expression step by step until it matches the original statement. If both expressions meet in the middle or become identical, then logical equivalence is proven. So for the second example, not P or Q and implies with implication law, it will become P implies Q, just like the previous example. In conclusion, the forward method start from the given statement, while the backward method start from the statement to be proven. Both methods rely on logical equivalence law and help us clearly demonstrate logical equivalence.
So let's move on to the next page. So logical equivalence. Logical equivalence only happen when two statements always have the same truth value. Is either will be true or both false under any conditions. Essentially meaning they say the same thing in different forms. So this is the symbol of logical equivalence. So we can do anything variable such as P logical equivalence to Q. So the words that the symbol that I arrow is equals to logical equivalence. Okay. Now let's move on to it. What does it means in logical equivalence? So it means if P is true, then the Q is also true. This is also can be contradiction with each other, such as if Q is not true, then P is also not true. It's going to be like that. So this is the symbol that commonly used by all of the people. So okay, let's move on to the next part, which is logical equivalence is apart by two things. There are so many things, but I only want to show you the tautology and the contradiction. So for the first part, the tautology is a statement that is always true, or proposition that is always true regardless of the truth values assigned to the individual variables. Okay, so to give you an example, P or not P, and also we have contradiction, which is a compound proposition that is always false regardless of the truth value of its components. Let me write it first. A statement that is always false. Okay. For an example to it is P and not P. Okay. Move on to our last step, and it's gonna be the method to prove the logical equivalence. So the first method that we have is truth table. Truth table and how it works is you're gonna list all the possible truth values for variable, evaluate each expression, compare final columns, and you can also compare truth values for each line. By lines. Okay. Now let's move on to our next method, which is logical laws. Wait, let me write it first. So for the logical laws, you're gonna apply non-logical identities such as De Morgan, implication, contrapositive to transform one expression into another. But basically means you're gonna transform them using identities. So yeah, that's all from me. We're gonna move to the next part.
Hi everyone. In this video, we will learn how to determine logical equivalence using truth tables. Logical equivalence means two statements always have the same truth value, no matter what values the variables take. I will show 3 example questions and solve each one step by step using a truth table. Let's begin. Example number 1. The question is not P and Q logically equivalent to not P or not Q? This example is also known as De Morgan's law. To prove this, we create a truth table listing all possibilities combinations of P and Q. First, I list P and Q. Then, I compute P and Q. After that, I take the negation separately. I compute not P and not Q. Then combine them using OR. As you can see in the table above, the highlighted columns are identical. So therefore, not P and Q is logically equivalent to not P or not Q. Now, we will continue to example number 2. In this example, we want to check the equivalence of an implication and its disjunctive form. The question is is P implies Q logically equivalent to not P or Q? There is a known identity that P implies Q is the same as not P or Q. Let's prove it using truth table. I start with P and Q, then I fill in the implication column. Remember, P implies Q is false only when P is true and Q is false. Other than that, P implies Q is true. Then I compute not P, and finally evaluate not P or Q. When we compare the last two columns, we see they are identical. Therefore, P implies Q is logically equivalent to not P or Q. Now, for the last example, we will prove that P by conditional Q is logically equivalent to P implies Q and Q implies P. This means the two expressions always share the same truth values. We will use a truth table to verify this. First step, I list all possible truth values for P and Q. These represent all combinations we need to test. Next, I evaluate the P implies Q. True implies true is true. True implies false is false. False implies true is true. And false implies false is true. Again, implication is false only when Q is true and P is false. I fill this column using the same rule. Next, I evaluate the implication P, Q. Remember that an implication is only false when P is true and Q is false. For all other cases, it's true. I fill in the column accordingly. Now I do the same, but for Q implies P. Again, implication is false only when Q is true and P is false. I fill this column using the same rule. Next step, I combine the two implications using AND. The AND operator is true only when both P implies Q and Q implies P are true. I fill this column by comparing the previous two columns row by row. True and true is true. False and true is false. True and false is false. And finally, true and true is true. After that, now I compute the biconditional P and Q. The biconditional is true when P and Q have the same truth value, whether it is both true or both false. I fill this column accordingly. Finally, I compare the last two columns, the biconditional and the conjunction of implications. As you can see, the truth values match all four rows. This proves they are logically equivalent. That's all for me. Thank you.
As for the conclusion, in summary, we learned that logical equivalence means two statements always share the same truth value. We proved this using truth tables, logical laws, and the forward-backward method through examples like De Morgan's law and implication equivalence. We saw how expression can be simplified and transformed. Finally, we demonstrate that P by conditional Q is equivalent to P implies Q and Q implies P. Logical equivalence is a key skill for simplifying expression, analyzing circuits, and building strong logical proof. So, thank you for watching our video.